In this video, we're going to go over some of the key ideas in section 1.2. I will assume that you also can read the section, so I won't go into a lot of detail on the problems in this slide deck that are also part of the examples and practice problems in section 1.2. But I do want to emphasize two main objectives of this section. One is to think about the different ways that we can describe patterns, and in particular, we'll be looking at patterns of numbers in this section. But we want to reflect on the different ways a pattern description can be given. And then secondly, for number patterns in particular, we're going to be using a mathematical notation called sequence notation that may be new to you, and so I want to make sure that everyone's reading and writing that correctly. So those are my two main takeaways. But so I'll show you some examples, and then I'll let you read the rest in the book. This is a good example of the kinds of questions that we can think about when we consider questions about number patterns and sequences. I'm going to pause the video and let you try to figure out what the next number is in each sequence, and then keep in mind that when you know what the next number is, that means that you also should be able to describe how you knew that, and then in a way that would allow someone else to then find the next term and the next term and the next term. So I'm going to count to 5 and then go on. So in the first problem, you probably noticed those are odd integers, and so it's fairly easy to see the next number would be 13, 15, 17, and it would be fairly easy to describe. But if you had to describe the pattern and didn't know the name of this collection of numbers, you might notice that the pattern was an adding pattern, meaning I'd add 2 for each term to get to the next term. So we might characterize that as by just saying my pattern here is add 2 each time. So if I told you that I want to make a sequence that starts off with a number 1 and adds 2 each time, you'd be able to generate this sequence for as long as you wanted to. Similarly, the second one has a pattern that's add 8 each time. We can do that by just looking at what we need to add on to go from one term to the next. The next one is interesting because there are a lot of different ways of thinking about that. Some of you may have recognized those as the perfect squares. Some of you may have become enamored with this idea of looking at the gaps from the first two problems and notice that the gaps here we're adding 3, then we're adding 5, then we're adding 7. So we're adding on successive odd numbers, or more directly, we're adding on numbers from this sequence to make a sequence. So that's a strange way of combining things. But if you notice that the sequence here are the perfect squares, then you're also likely to have said, well, the first term here is 1 squared, second term is 2 squared, third term is 3 squared, the fourth term is 4 squared, and so on. And so we could say the nth term is n squared. And when I write that, I'm thinking of the n there as being a variable. I'm thinking of that as a sentence where I can read it as the first term is 1 squared, or the second term is 2 squared, or the third term is 3 squared. So I'm seeing the connection between the position of the term and the formula that tells me what the term is. And so a better way of writing that would be with the sequence notation, a sub n equals n squared. Now in this notation, the letter a here is the name of the sequence, so that's not a variable. I know it's a letter, but it's not a variable. We will never plug in a number for a, but the letter n is the variable, and for n we want to plug in the numbers that represent the positions of the sequence. So when I say a1 is 1 squared, that's shorthand for saying the first term is 1 squared. If I say a2 is 2 squared, a3 is 3 squared, and so on, it's shorthand for saying the nth term is n squared, but I can do it with a formula, and the idea that in that formula, the letter n can represent the numbers 1, 2, 3, 4, 5, and so on. It's not terribly different than in calculus world when you write f of x, something like this. In that notation, just like in our sequence notation, f is not a variable, it's just the name of the function, and the x stands for an unknown number that can become any number if you want it to be. So you can plug a number in for x and then read that off. So the sequence notation really is just a different sort of discrete math version of function notation from calculus world. Okay, so continuing on in our sequences, we see here that the pattern and 4 and 5 become multiplicative. In other words, to go from one term to the next, I'm not adding on, but I'm multiplying by, and there's nothing wrong with that. And finally, the last one is probably the trickiest one. We also are multiplying each time, but here we're multiplying by 2, and then by 3, and then by 4, and then by 5, and so on. So that's a little bit harder to spot. These terms have a name that we will use later on in our class. The formula for the sequence would be, let's say I call this sequence B. We would say B sub n is n factorial. That's n with an exclamation point. And n factorial means to multiply all the numbers from n down to 1. And so, for example, B sub 4 will be 4 factorial, which is 4 times 3 times 2 times 1. And if you do that, you get 24, and you can see that is sure enough what's happening there. The fourth term is 4 factorial, so in general, the nth term is n factorial for this. Okay, so that gives us a set of examples. I do want to point out the difference in the way we're describing these things. In questions 1, 2, and 4, we're explaining how to get the next term from the previous term. Whereas in 3 and 5, at least the way I've written them over here, I'm providing a formula so that if you just tell me which term you want, I can tell you what that number would be. So if you wanted to know the 10th term, for example, in number 3, the 10th term is going to be 10 squared, or 100. Down here, the 10th term is going to be 10 factorial, which you may need a calculator to figure out. It's north of 3 million, but we can do it. For these other ones, the only way I'd be able to get the 10th term is by, what do I got here? 1, 2, 3, 4, 5, 6. I would need to get the 7th term, then the 8th one, then the 9th one, and then the 10th one. And so that's how I would have to get the 10th term in examples 1, 2, and 4. So when we have a pattern that we're describing by what I do to previous terms to get the next term, we call that a recursive description. So 1, 2, and 4 descriptions here are recursive. And then the description I have over on the right side for 3 and 5, we're going to call those closed formulas. In other words, it's a formula that I can just plug a number into and get a number back out that answers the question of what term would be in that position. All right, so let's practice writing the notation in those two ways. You'll see there's a third type of description that if you ask people to describe these things, they'll sometimes say this. It's not particularly helpful for us, but I did want to acknowledge that it's a possibility. So for example, as we said before, this is just a set of odd numbers, and I think most people know what that is. And so if you saw that sequence, you might say, well, that's the set of odd numbers. That doesn't really help us for either bullets 1 or bullets 2, but it is in fact one way that people could identify the sequence. So you'll see me mostly ignoring this third bullet. But our main goal is to understand the difference, the way we're thinking about it, between the first two things. Okay, so remember, when I am referring to these values, I'm thinking of that first number as being A1, then A2, then A3. So when I write that, I'm thinking about it as the first term, the second term, the third term, the fourth term, the fifth term, and then those values are 1, 3, 5, 7, 9. So the recursive formula, as we said before, it should have something to do with adding 2. So I would write that as saying, well, like the second term is 2 more than the first term, and the third term is 2 more than the second term, and the fourth term is 2 more than the third term. So that's how I can convey that I'm always adding 2 to the previous term to get the next term. But obviously I don't want to write that for every single value. I want to write something more general. And so I would write this as a sub n, meaning a generic term, so n could be any of these things, is equal to 2 plus, and then I want to be able to write the previous term. So if I write A2, the previous term is A1. If I write A3, the previous term is A2. So the previous term is always another A, another value of A, but now the subscript If it's the previous term to the third term, that means the subscript should be one less than that subscript. So if I want a sub n to be the generic term I'm looking at, the previous term would be the term with the previous number subscript. So that n minus 1 is in the subscript of the a, and it refers to the term before the nth term. So this way of writing a sub n is 2 plus a sub n minus 1 captures for all n the fact that I'm always adding on. Now, for that to be a complete description of the sequence, I also have to say how the sequence starts. The one term that the recursive description doesn't help you with is this one. That term is not 2 more than anything. It's just the first number. So if I don't tell you what that is, then you can add 2 and add 2 and add 2, but you don't know where to start. So I need both things. So what you'll see me say that I have this pattern of adding on 2 for all of the terms starting with the second one. So I'll say starting with the second term and going forward, that's the pattern. But if you ask me about the first term, I'm going to say that it's a1 equals 1. So this is a complete recursive description of the sequence, and I really do need both parts. I need the pattern, and I need to know where it starts. Now, the close formula for this is not too hard. And in fact, anytime the sequence is one of these things where we're just adding on, these are called arithmetic progressions, but anytime I'm just adding on a constant number each time, then the formula is actually pretty straightforward to find. Here's the way I would recommend you do it. There are more than one way to do it, but this way I think pays off more for other types of sequences. So I'm going to form another sequence that are just the multiples of 2. And so if I just look at multiples of 2, I'm going to have 2, 4, 6, 8, 10, and so on. The a sub n sequence is the one I don't know. That's the thing up at the top. So that's 1, 3, 5, 7, 9, and so on. So I'm writing down my unknown sequence, a sub n, right underneath a known sequence, b sub n. Now, how did I know to pick the multiples of 2? Well, I'm picking a sequence that has the same pattern, has the same growth pattern. Not the same starting point, but the same growth pattern. So the multiples of 2 are a very easy pattern that have that same, a very easy sequence that has the same pattern. Multiples of 2 are going to have the pattern add 2. If I were trying to find a formula, if I'm trying to find a sequence that has a pattern of add 3, then multiples of 3 would do that. So I kind of know ahead of time that is going to be a sequence that has the same growth factor and just a different starting position. So if I compare these two, I can see that the bottom numbers are 1 less than the top numbers. 1 is 1 less, 1 less, 1 less, 1 less, 1 less. And so that means my formula should be the formula for the top thing minus 1. So I can just compare the sequences and then adjust the formula for the one that I know the formula for. So this would be a closed sequence, a closed formula. Like I said before, if I wanted to know the 100th term, a sub 100, I now know that that's going to be 2 times 100 minus 1, which is 199. So in this sequence, if you ask me what the 100th term is, I know that it's 199. With this description, if you ask me what the 100th term is, I would have to come back to here and find the 6th term, the 7th term, the 8th term, the 9th term. I have to work my way all the way up to the 100th term to be able to find it. So you can see how this, even though this required a little more work to find the closed formula, it is a more useful thing to have. So we're going to focus on both of these. In particular, we want to be able to go back and forth between these to the extent we can. You will find that if you give me a closed formula, I can always tell you what the recursive description of that would be. But if you give me a recursive description, it could actually be a lot of work to find the closed formula, and there are actually some times where you can give a very simple recursive formula where there is no closed formula. So going from closed to recursive, we can do all the time based on our algebra skills. Going from recursive to closed is going to be a hard problem that we're going to have to work on throughout the course. So I'm going to stop there, and I'll post a couple more examples from the remainder of the slides, but this is the basic idea of this section.